In the previous lessons, we talked about how to design circuits using elements such as resistors, capacitors, and even LEDs. You might be wondering, how do we go about designing circuits that are made up of zeros and ones? The answer is using logic. Logic is a stateless way to calculate consistent results with the same input. In other words, logic systems always take inputs and give out answers. The way that we define and analyze logical systems is by using logic gates and Boolean algebra. Boolean algebra is essentially the algebra for logic. It's exercising mathematical models using logic gates to analyze the behavior of digital systems. The advantage of this is that it's easy to use for computers due to the compatibility with binary. So what is logic? In actuality, you've encountered it every day in your daily life. Logic in Boolean algebra consists of simple logic functions such as not, and or. Here are some of the fundamental terms of Boolean algebra and logic. So the logical operators are the functions. They're essentially the same as mathematical operators such as addition, subtraction, and multiplication, except for logical systems. A logic gate is a representation of a logical operation, and combinational logic is equivalent to a circuit except in a digital system. It's defined as a combination of logic gates that perform a complex logical function. Here are the notations for the most common logical operations: not, and or. As you can see, and looks very similar to some multiplication notation that you've seen, and or looks very similar to addition. And the main thing to keep in mind is that we're only analyzing between two states. Yes, true, high, 1 all mean the same thing, and no, false, low, and 0 all mean the same thing. So here are the different symbols for some common logical operations. As you can see on the top one, and is drawn with 2 inputs and 1 output. Its algebraic function is given as the output equals A and B, or A dot B. One way that we can analyze these different logical operators is by drawing a truth table. This is very useful in analyzing and observing digital systems. A truth table, which is the last column in this graph, is essentially all the combinations of outputs with respect to all the combinations of inputs. So generally on the left side of the truth table, you draw you list all of your inputs. And then after you list all of your inputs, which in this case are just A and B, you list each combination, all possible combinations that could occur with those inputs. Since we only have two different inputs, the only possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And as you can see, all the rest of the listed logic operators have 2 inputs except for the not operation. We'll talk about how to derive the outputs of these different logical operators very soon. The not operator means opposite. It's basically an inverter. Whatever you put in, you get the opposite out. If you put a high in, you get low out. If you get low in, you get high out. The logic operators are actually very intuitive and can be used in natural language very easily. For example, you can use a very simple sentence like I am happy. You can essentially input the logical operator into that sentence, and you can naturally see how this occurs in natural language as well as in binary logic. The next logical operation we're going to talk about is AND. And in the same way that not can be used in natural language, this can be too. So we're going to help build your intuition around this by using the sentence illustrated in this slide. It says, you can buy a new car if your dad and your mom say okay. So the output of our logical operation is if you can get a new car. So zeros are no and ones are essentially yes. So again, this is considered what we call a truth table. And again, on the left side of the truth table, we list both of our inputs and every possible combination of those inputs. So now let's input each of these possibilities into the sentence that's given and see how we get the outputs. So in the first case, we say that both your mom and your dad say no to you having a new car. So since both your mom and your dad say no, that means you can't get a car. In the second case, your mom says no, but your dad says yes, but you still can't get a car because both your mom and your dad have to say yes. So in the third case, your mom says yes, your dad says no, ultimately you still can't get a car. Now for the last possibility, your mom says yes and your dad says yes, therefore we get a 1 in the output, and you can get a new car. The last of the most common logic operations is called the OR operator. We're going to use the same sentence that we used before, except we're going to input the OR operator in place of AND. So let's view the first combination of inputs and outputs. So in the case where your mom and your dad say you can't have a new car, we know that the output is still going to be no. So, but given that only your mom or your dad have to say okay, all we need is one yes or one high to get a high on the output. So you can see that for each of the other potential combinations, we get a 1 because there's at least one 1 in the input column. So again, that was just to build your intuition. This is a more practical example of the truth table and how it looks more often when you're analyzing digital systems. So you usually have an input A, an input B, and some output. And as you can see that this is definitely the OR operator because it has a high for every instance where there's at least one high. Logical expressions are simply the equations for digital systems. Any logical expression can be implemented with nots, ands, and ors. And ultimately, you use Boolean algebra to potentially solve for inputs and outputs, or to be able to simplify a system of equations. Let's give some examples. Let's say I have an equation or logical expression that said A plus B equals, or A or B equals 0, what can we say about our inputs A and B? Since we know that if either A or B is high, that will give us a 1, we know that both A and B have to both be low for this equation to be satisfied. In the same way, we can ask, what about in the case what if we had an expression that looks something like this? A plus not, or A or not A is equal to what? Since we know that only one of these has to be high for the output to be high, we can automatically assume that this is high, because even if A is low, then not A is high, and if A is high, then the output is high regardless. So as one final example, let's say you have an expression that looks something like this. What would be the output of this expression? So let's break it down piece by piece. So this is A and not A, or B and not B. Since we know that for the AND operator, both inputs have to be high for the output to be high, we can automatically assume that this is low, because one of these has to be low. In the same way, one of these has to be low because it's one input in the inverted of that same input. So since both of these are low, we can assume that the output is low.